Sphere on an incline. A sphere with a mass m and a radius r rolls down an incline that makes an angle theta with the horizontal. The moment of inertia of the sphere is 2/5 mr squared. The sphere rolls without slipping. On the diagram below, draw and label all the forces, not the components, acting on the sphere as it rolls. Clearly indicate at which point on the sphere the force is acting. Part B. As the sphere rolls down the incline, which force causes a change in its angular velocity with respect to its center of mass? Briefly explain your reasoning. In terms of m, r, and theta, and fundamental constants, determine the minimum force of friction necessary to keep the sphere rolling without slipping. In terms of m, r, theta, and fundamental constants, determine the acceleration of the sphere. Part E. The sphere is now replaced with a cylinder of the same mass and radius. Will the cylinder have an acceleration greater than, less than, or equal to the acceleration of the sphere? And you can choose one of the three there, and briefly explain your reasoning. Part A. The normal force is perpendicular to the sphere-incline interface, right over here. The gravitational force acts in the downward direction, as always. Both forces act on the sphere's center of mass. The static friction force acts at the sphere-incline interface and is pointed up the incline. So that's over here. Do not draw that at the center of mass. It's where it makes contact, where the sphere makes contact with the incline. Which force causes a change in the angular velocity? That would be the static friction force. Because the normal and gravitational forces pass through the center of mass, the friction force is the only force that can create a torque about the center of mass. Right? These two forces act right at the center of a mass, providing zero torque. Friction force is a distance r away. The torque creates an angular acceleration about the center of mass, resulting in a change of angular velocity. Determine the minimum force of friction necessary to keep the sphere rolling without slipping. When an object rolls without slipping, the friction between the object and the surface is static friction, as the velocity at the interface point is zero. When the maximum static friction force is not great enough to maintain the zero velocity at the interface, then the object slips. At the point where it starts slipping, A that equals R alpha is no longer valid. The minimum force to start the slipping is where that condition just barely holds. Calculate using Newton's second law in linear and rotational forms. The simultaneous equations resulting from the calculations will provide the solution. Time to do the math. So let's follow the numbers. 1. This is your linear Newton's second law. The sum of the forces is equal to ma. You have gravity pulling it down and static friction trying to keep it up. That equals ma. So now let's go over to rotational. That's where the sum of the torque is I alpha. We only have one torque due to friction. Here's I, and alpha we can immediately substitute. Alpha is equal to A over R because we want it not to slip. Calculate that out. You get the static friction force is 2/5 ma. Now go back over to linear, follow this line here, and substitute in the static friction force. So now we have mg sine theta minus 2/5 ma equals ma. Solve that for acceleration, and here's our acceleration. And one final step, we want to find the static friction force, the minimum force. Follow this arrow. We have the static friction force is 2/5 ma. We have found acceleration, substituted in, and here's our answer. And I'll go ahead and erase all those marks, and you might want to pause it at this point and follow the arrows and find the final friction force. Determine the acceleration of the sphere. Actually, parts C and D are backwards. You should calculate the acceleration first and then find your force. but that's okay. We're going to do this again. It is very good practice. So we start with our linear equations. Sum of the forces is ma. The only two forces are mg sine theta and friction force. That equals ma. That's the first step. Now go over to rotational. We sum up the torques, and there is only one torque provided by the friction force, and that's 2/5 mr squared, and we replace alpha with a over r as it is not slipping. And just calculate this out, we get the friction force is 2/5 ma. We substitute that in to the linear equation. We get this, and then we just simplify that and we find the acceleration is 5/7 g sine theta. We now have a cylinder. Will it have an acceleration greater than, less than, or equal to the acceleration of the sphere? We're going to choose less than because the cylinder has a moment of inertia greater than that of the sphere. Since the moment of inertia is inversely proportional to alpha, the cylinder will have a smaller alpha. The object is not slipping, so alpha is equal to a over r. Thus, the cylinder will have a lower acceleration.